Welcome to the timing side channels session. Only one announcement again. The first talk is postponed at least. And we do the talk that we postponed this morning by Steffan. And then we return to the usual schedule of the timing side channels session.
There's a little bit of timing channel possibility in here, so I think it can kind of fit. So this is probably not too much of an interesting statement or surprising statement for most of you in here, but module systems, they're hard. And if it's a distributed system, probably just doubly so. For example, think we have Alice who wants to send a message to Bob. So she sends a function f, which depends maybe on some module on her machine too, to Bob. Bob doesn't know it, so Bob might then just ask Alice, can I please also get this module, because otherwise I cannot run your code. And Alice obliges, sends Bob the code. But hopefully then Bob would actually has cached somehow this module. So when Alice later is going to send a different function g to Bob, then Bob doesn't actually have to ask a second time. So if we, instead of having everything being sent by value, we might want to have function closures being referencing different things based on like a hash instead. And based on that, we can maybe then improve the network traffic and make things run faster that way. And actually, it's not just modules, it's any kind of dependency that you might have in this kind of a function closure. Thank you. Charlie is now going to be somehow branching on some secret, and if so, machine that Mallory wasn't actually supposed to. So you will still need to remember to also downgrade the things you're going to be caching. Finally, for availability, currently in the distributed systems we're going to be looking at, everything is being sent by value, and that has a nice property. That so if Alice is going to be sending this function f to Bob and then kills her machine, and Bob then also forwards again to Charlie and then kills his machine. And Charlie forwards further on, killing the machine, and so on until we get to Zoe, who is then at the end actually wants to execute this function. If we're adding this caching in, or we're beginning to add some references to modules and stuff in, we could run into an availability issue, as in how can I actually execute this function when the origin actually isn't available anymore. So that is still something that we want to be preserving. And all in all, the question we were asking previously then actually boils down to how can we add an information flow aware cache inside of a distributed system. In particular, though, for our case study here, we are looking at the Troupe programming language from Aarhus University by Aslan, Askarov, and others, which kind of looks like this, an SML programming-like thing with additions inspired by Erlang and a few other places. So this gives you the ability to actually do decentralized programming, so distributed systems that are truly open. You can join with any code you kind of want, and it organizes by itself. It also then includes information flow control to actually provide read and write permissions on the types of every value. And whether these read and write permissions are actually violated is then ensured by a monitor at runtime. It's a monitor because the programming language by itself is also made dynamically typed, because otherwise it would be difficult to have a system that can actually be truly updated with new code, with new types that you've never seen before, and have systems interacting where they don't actually know the code of the others. So when we're looking at this question, what we are actually trying to think about is, can we do this with the minimal extension to the trusted computing base? Because hash maps or caching is just difficult. That is, there's thousands of examples of that being the case. And in this case, if we don't want to extend the trusted computing base, we need to implement it in some other way. But we already have a programming language that does deal with information flow. So maybe can we do this by actually using Troupe itself in this use case? Based on at least our first prototype here, if we look back in the first example with Alice sending something to Bob, we have now implemented a cache inside of Troupe itself, which is then running as a separate thread, run by the trusted computing base. So when Alice wants to send a message, the trusted computing base is going to send that message to Bob with some dependencies only referenced by hash rather than actually sent by a value. At the same time, Alice is also going to be sending a set message to her own cache thread, which is then going to be storing this value down, storing this value. Bob is then going to be looking at his own cache thread, whether there's actually something stored here, which then also is going to give you something back. Maybe there isn't anything cached, or there is something cached. If something is cached, we're done, and we got the nice performance increase that we wanted. Otherwise, the trusted computing base can then send a miss message back to Alice, and Alice will then look up in her own cache and find that value for Bob. And in which case, Bob can then actually fully deserialize the message and run the code given. And remember also this for later, such that for another time around, when this dependency is missing at a different time, Bob can just insert it himself. This thread, the code actually needed for making this cache thread in Troupe was actually very, very tiny. So we needed like a few lines of code to like take the SHA string and turn it into like a 32-bit integer. We needed only like 20 lines of code for actually defining the thread that manages the hash map, the cache, where we then have implemented a hash map inside of Troupe, which we can get back to that, but we need to probably recreate or redo that one from scratch, but that's a different thing. But in terms of like the interface, it's just purely like inserting with into the map the authority and then the key value pair. So the interface is very similar to the other usual things you would have in a programming language like this. And then we need a little bit of a public interface for the trusted computing base entry points, so the setter and the getter, which are going to be dealing with sending the messages. And finally, there's, because we're in the timing part now, there's a little bit of a wrapper for the sandbox feature of Troupe, which will also try and see if we can mitigate some timing attacks. The hash map itself, based on the current prototype, what we have come up with at least is a little bit of a specification for how you would like to have this hash map work. So if we think back to like the previous, one of the previous examples we had, Charlie is forwarding some function f to Bob with some dependency on some module. And this is secret at Charlie's level. And here Bob might say, I don't know this, I'll give a miss on that. If Alice later is going to also have a same dependency sent to Bob, Alice should also be given a miss, because otherwise she would know that Charlie had sent that message. But Alice is sending it at the public level, so when Dorothy is going to be sending a message to Bob, even if it's secret at Dorothy's level, this is okay to actually be a hit, because it's fair enough that there's going to be information flowing from Alice's public message to Dorothy in this case. So in terms of like how the hash map should be designed, it should be like a single data structure with public, where you can put in public and secret key value pairs. And then it can provide information flow aware projections of the entire insertion operations history. So you have some history here. You insert x is equals to 1 publicly. You then insert x equals to 2 at Alice's level. And then y equals to 3, and removing x again at Bob's level, and finally inserting y is equals to 4 at the public level. If you want to project this to the public level, you will just get the insertions at either end. If you're going to be seeing go for Alice's projection, then you would actually see this override of x is equals to 2. And finally, if you go for Bob's level, we will see x is equals to, x has been removed, but also y still equals to 4, because this insertion is newer than the previous insertion. And following a specification like this would give us essentially one data structure that gives us this behavior that we want. Is as far as we can see. Any questions on this? Maybe my example didn't work out. I see a few confused faces. Okay, we can take that later maybe. In terms of what actually we have identified needs to be part of the trusted computing base, the miss and misreply messages you saw earlier, where you were like, I don't know this, can you please send it to me? That has to be sent by value, so that shouldn't be using the dependency system as part of the resolving the dependency system. So that might need to be part of the trusted computing base. Also, it seems to us right now that we would want to have extracting or inserting the dependency should be done as part of serialization and deserialization. And that requires introspection of functions and their closures, which isn't something. Reflection might not be something you want to have as a language feature. So in that case, you want to have it as part of your trusted computing base. And similarly, hashing some values would also have to be in the TCP, because if you're hashing a function, you need to hash the source of that function, or the bytecode or something like that. And finally, also, the scheduler or the interpreter in that case, whatever is running the code at the end, also needs to have a little bit of refactoring, maybe, such that you can actually run code from a TCP context. Until now, at least, in this case of Troupe, at least, the problem has been that you could only run Troupe code from Troupe code, but now you also need to run Troupe code and wait for the result of Troupe code from the trusted computer base itself. So all in all, we had this question: how can we actually add an information flow aware cache? And we hope at least the answer is, based on our prototype, based on everything you've seen, the answer can be that you can actually do it by bootstrapping the information flow aware runtime. Thank you.
So we have time for questions.
So I understand the kind of partial views that you give to different users, but how do you avoid timing attacks?
Very good question, yeah. So there you go. Troupe includes at least a sandboxing feature. Could probably call it more a timeboxing feature, where you're giving it a function f and a time t, and then it will guarantee you that you will, it either will return the result of having run that function, it will pad the time needed such that it actually takes the entire t time you want. Otherwise, it gives you an error if there's something crashed. Then it will tell you that this crashed in this time, or it will give you a continuation such that you can continue running it if you want to run the computation that takes longer than the t time you gave it. It seems right now that just using a t of 1 millisecond, which was the lowest I could set it to, was more than enough, because the hash map just never took longer than 1 millisecond to actually insert and extract something. So yeah, based on, I can't remember what the actual term for it is now, but by padding essentially the running time, such that it always takes 1 millisecond exactly, it seems to at least work for now.
More questions? So in terms of cryptography, is it just about using hashes, or in general, what kind of things do you use in Troupe?
Are you thinking like as in like how to reference the different Troupe values? Or what were you thinking about, like what we're using? I'm sorry, I'm not entirely understanding the question.
So I guess you must use encryption, signatures, things like this to implement this IFC in terms of something distributed.
As far as I understand, with distributed systems, I'm also just switching over to this topic, so please, if someone can correct me, that would be nice. What are usually pointers is when you think pointers on usual machines in distributed systems, you always say cryptographic hash. So that's where we were thinking to begin to use a SHA string of the value. And otherwise, everything is built on top of a peer-to-peer library, which also includes lots of cryptography to actually ensure that you're actually speaking with the other peer you actually wanted to speak to, and no one was like trying to impersonate someone else. Yeah. So there's a lot of cryptography going on underneath. Luckily, most of it we don't. We just use.
Thank you.
Yeah.
Okay, so if there's not more questions, we stop here and the next speaker can prepare.